Hello, welcome to today's introductory session on spectroscopy. Basically, in today's session I want to talk about the nature of radiation, which is a very crucial component of our understanding of spectroscopy. And the session is planned as follows, that is, I will first try to talk about what exactly we mean by spectroscopy, then we will try to define what is electromagnetic radiation, and then we will try to make some kind of a visual understanding of what exactly we mean by that. Then we will take up the characteristics of EM radiation, that means how do we characterize EM radiation and what is the significance of each one of the characteristics there, and then we will try to sum up what we learned today. Let us make a beginning by defining what is spectroscopy. Spectroscopy may be defined as the study of interaction of radiation with matter, and is used for, and this interaction study is used for structural elucidation, quantification and interaction studies. Let us understand what is the meaning of this. Basically, in spectroscopy what we do is we take radiation of different possible types. We will learn about that as we proceed a little further, and then we take matter and we study how does the radiation and matter interact and what happens as a consequence of that. So, spectroscopy essentially is a consequence of the interaction between radiation and matter, and this interaction will depend on what kind of radiation I am talking about and what kind of matter I am dealing with. So, both of them are going to determine the consequence or the outcome of such an interaction, and this outcome is used primarily for structural elucidation. That means, suppose I have got an organic molecule, I want to know the structure of that one. So, what do? I study its UV visible spectrum, or studies IR spectra, studies NMR. So, we will talk about all this as we proceed. So, these are the spectroscopic tools. So, we will try to interact this molecule with different types of radiation and see the resultant of that. That resultant is used to decipher or to work out or to elucidate the structure of the molecule. And second important kind of significance or application of spectroscopy is in terms of quantification. That means, typically as we know that in case of chemistry, we got one is a big qualitative aspect of things. So, that is structural elucidation is one bit of that, and second aspect of it is quantification. We want to find out what is the composition of a given thing, and that means in terms of what all the constituents are there. The second thing is we want to know how much of each one of them is there. That again can be determined in terms of using the spectroscopy. And thirdly, the most another very significant component or an application of spectroscopy is in the interaction studies. Now, suppose I want to study, you have a protein molecule, you got a DNA. Now, suppose I take the two together, how do they interact? Now, suppose I want to talk about, say, a drug. How does a drug interact? How does a drug interact with suppose there is a pathogen in the body. So, if I take some kind of thing, how does it affect? So, basically some kind of interaction between two different kind of species can be studied in terms of spectroscopy. So, what we do is we look at one species, understand that, look at a spectroscopic behavior, make the other one come in closer contact with them, and then see what happens. Does the interaction change? If yes, to what extent, in what way? So, all these are the domains of spectroscopy. So, spectroscopy is probably the most vital component of any scientific endeavor, irrespective of what subject we are talking about. It is not necessarily confined to chemistry. You can go to any domain. You start from, you go to life sciences, you go to biochemistry, you go to immunology, you go to any area, physics. You talk about geology, you talk about astronomy, everywhere spectroscopy has a role to play. So, it is a very, very broad area of work which we want to take up. Okay. With this introduction to spectroscopy, let us be very clear here. Please mark it that we are talking about the study of interaction of radiation and matter. To understand that, we need to know what is radiation, we need to know what is matter. So, that is the way I am going to proceed in this particular topic. So, today we will talk about what is radiation, then we will take up later on what is matter, and then we will take up in the third stage how does the radiation and matter interact. So, that is the way we kind of logically built up our understanding of spectroscopy. Okay. Now, let us come down to what is electromagnetic radiation, or radiation broadly is used as such. Electromagnetic radiation basically is some kind of a radiant energy which is transmitted through space at enormous velocities. The sunlight coming to us is electromagnetic radiation. The light from bulb is electromagnetic radiation. The UV radiations which are harmful to us, which our ozone layer protects us from, is an EM radiation. X-rays we use for our analysis, kind of diagnosis purposes, is an EM radiation. So, there are wide variety of them. Today we are using mobile phones, so that microwaves are used there, they are again electromagnetic radiation. So, electromagnetic radiation is a very, very useful component or tool in hand of our scientific community, or even for layman, radiation has a role to play. You must be hearing nowadays that we are talking about the mobile towers or causing radiation problems. So, that is exactly the radiation we are talking about, because it can have good effect, it can have bad effects as well. Okay. Then as I said, they transmitted through space at enormous velocities. The velocities are to the tune of about 3 into 10⁸ meters per second, which is an enormously large velocity, and that is the kind of velocity we have in vacuum. But if it transmits in medium, then velocity gets changed a bit. Then it does not need a medium for transmission. It does transmit through medium, but it is not required. Even if the total vacuum is there, EM radiation can pass through that. So, that means that is the kind of quality it has. Let us now see how does an EM radiation look like and how do we depict that. Essentially, if you look at an electromagnetic radiation, is a kind of an electromagnetic, as the name suggests, electromagnetic. It is an electromagnetic disturbance. That means what happens is, you can visualize like this. Suppose this is the direction in which my radiation is going, and this thumb is the direction of electrical vector. So, essentially what happens is, suppose I am saying a radiation is moving from here to this direction. So, essentially there is electrical component which is moving like this. This is kind of a sinusoidal wave which is moving in this direction of propagation, but this is perpendicular to the direction of propagation, and then there is a magnetic component. The blue component here essentially is the electrical vector which is moving in a sinusoidal way, and the red one here depicts what is called as the corresponding magnetic component. So, it is an electromagnetic disturbance in space. Okay. Let us try to have a look at a small animation here. So, this is the way probably you can visualize. You can visualize that a kind of a wave is coming towards you, wherein the red thing here, the red wave essentially depicts the electrical component of the wave, and the green one depicts the magnetic part of it. So, what you can observe very carefully, that as the wave is moving from far towards you, what you are seeing is that the two components, the electrical component and the magnetic component, both are running perpendicular to each other as well as to direction of propagation. So, essentially it is an electrical and magnetic disturbance or fields which are travelling in the plane perpendicular to each other and also to direction of propagation. There are a number of characteristics used to identify, there are characteristics which are identified with the electromagnetic radiation. Let us understand what are the characteristics by which we can ascribe to the EM radiation. Let us look at that. The first one is called as amplitude. Amplitude essentially it refers to the maximum height to which the wave oscillates and equals to the height of the crest or depth of the troughs. What it means is, you just saw that there was a wave moving like this. Now, when the wave is moving, so to what is the maximum height to which it goes? What is the minimum there? So, maxima of the kind of crest and minima of the trough. So, this is the meaning of amplitude, and it is a measure of radiant power and the intensity of the radiation. Let us again have a look at that animation I referred to. So, what we see here is the same EM radiation I showed you earlier. So, what you are finding here, okay, let me do one thing, let me just put off one of the radiation, that is one I am just putting off the magnetic component, and also let me try to kind of slow it down a little. What you see here is that the wave is coming towards you from a far towards you. Now, what I am going to do is, there is a control here by which I can change the amplitude here. What you see is, right now amplitude is some 5 units. Let me make it more, say 6, 7, 8, 9, 10. So, what you are seeing is amplitude basically refers to what is the height of the wave, okay. And as I just mentioned that this amplitude is a measure of the power, because we said that EM radiation is a radiant power. So, if there is more amplitude, there is more power behind it. You try to imagine it, suppose you are on seashore, a wave is coming, suppose a small ripple is coming, it does not have too much of power, but suppose a big wave comes, it carries a lot of power with it. So, that amplitude, the maxima of that is a measure of the power which the wave is carrying along with that. So, amplitude is a measure of radiant power and the intensity of the radiation. I am using two terms here, one is radiant power and second is the intensity of radiation. Let us try to differentiate between the two, because the two are very, very important terms for us. The radiant power refers to the energy of radiation striking at a given area per unit time. Suppose I am looking at this area, radiation is coming striking on this area per unit time. So, what is the rate at which it is striking here? That is the power, radiant power. So, and this is measured in terms of the square of the amplitude. Higher the amplitude, the square of that will be still higher. So, that will be the power of that one. On the other hand, if you want to look at the intensity, so it is defined as the radiant power per unit solid angle. That means, when the radiation is coming on a small particular 1 unit angle, what is the part of it? What is the intensity of that? How intense is the radiation? Okay. So, these two terms are closely related, but one must be clear about what do you mean by radiant power, that is what is happening per unit area, per unit time on a given area, and intensity is what is happening at per unit solid angle. So, there two are different things. Another characteristic of AM radiation is the wavelength. As the name suggests, wavelength, that means length of one wave. So, in other words, if I am trying to show a wave, so it is a linear distance between two consecutive wave crests or wave troughs. That means, you have got two maximas, see the difference between the two, that is a wavelength. Two minimas, take the difference, or you start from any one point on the wave and look for an equivalent point. So, that distance happens to be the wavelength. Let us see it pictorially. So, you can see that this is my lambda wavelength, maxima here, maxima here. You can have minima here and minima here, or some zero amplitude here, a zero amplitude here. So, this also is the wavelength. Okay. So, that is the way we define what is the wavelength, length of one wave of the radiation. Now, this wavelength, as the name suggests, it is a length of some kind. Okay. It is represented by a Greek letter lambda, that is the typical symbol given to wavelength, lambda, and it has dimensions of length as the name itself suggests, it is a wavelength. And then it is typically expressed in terms of meter, that is a SI unit of length, and then we got the corresponding prefixes put to that. That means, you have centimeter, micrometer, nanometer or angstrom. Basically, it is expressed in having the dimensions of length, expressed in terms of meter and the corresponding smaller units there. Centimeter, that means 1/100th of a meter, micrometer is about a 1 million times 1 millionth part of a meter, nanometer is 10⁻⁹ meter, angstrom is about 10⁻⁻10 meter. So, that is the kind of units we use it here for. So, that is the typical conversions I am just referring to. Angstrom is 10⁻⁻10, nano is 10⁻⁹, micro is 10⁻⁶ meters. Yet another one, the third characteristic of our EM radiation is the frequency. Now, how do we look at frequency? Frequency basically is defined as the number of wave crests or wave troughs that pass through a given point per second. Now, what does it mean? Now, suppose I am looking at this point of my reference, a wave is coming, moving like this. So, how many times does a wave crest or a wave trough pass through this per second? So, that is the frequency, how often the wave is able to reach here. Okay. And this actually is represented in terms of a letter called as nu, that is a symbol given to frequency, and it is expressed in terms of second inverse or per second or hertz, that are units of frequency. That means, by definition, how many wavelengths per second. So, per second is the unit for frequency, and wavelength and frequencies are related, but obvious. That means, frequency is c, that is the velocity of light, divided by wavelength. So, we just said the frequency and wavelength are related, inversely related rather. As the wavelength goes up, the frequency goes down and vice versa. Let's try to have a look at it. The current animation here is with a wavelength of about 5 units on this particular software. Now, suppose I increase the wavelength, rather decrease the wavelength. Let's see what happens. I am decreasing it to 4, to 3, to 2. So, what you are seeing is that as I decrease the wavelength, then what happens is the number of waves, because then the length has become less, because in this particular animation the total length is fixed, the start of the animation to end of the animation. Since the distance is fixed, so I have decreased the wavelength. So, the number of waves which are coming through, which are, you can see it as an arrow here which is coming towards you. So, this the frequency becomes large, more. So, there is a relationship between frequency and the wavelength, there is an inverse relationship. The next parameter, the characteristic of our EM radiation happens to be wave number. Now, this equals the number of waves per unit distance. Now, we just showed this animation when we are trying to relate frequency and wavelength. You can see that when the distance was fixed, so what is happening is, if the number of waves, suppose I take this to be 1 unit distance. So, when I decrease the wavelength, the number of waves became more. So, the wave number is that. Okay. So, if the wavelength is large, there are lesser number of waves in that particular distance. So, wave number and wavelength again are related. Let us try to see. This is the reciprocal of wavelength expressed in terms of meter. So, the symbol of wave number is nu bar, and nu bar is equal to 1 by lambda. Okay. So, the wave number is number of waves per unit distance, and that is the kind of relationship we have. That means nu bar is equal to 1 by lambda, where lambda is the wavelength. So, as wavelength goes up, wave number goes down. As wavelength goes down, wavelength goes up. So, again it is a inverse relationship. Typically, since it is inverse of wavelength and wavelength is given in terms of meter, so the unit for wave number will be meter inverse. Meter inverse actually is a unit which is technically speaking the right unit, but centimeter inverse is the most commonly used unit for wave number. Typically in IR spectra we will be using so many centimeter inverse, Raman spectrum also use centimeter inverse and things like that. And then as you just mentioned, the wavelength and wave number are related as inversely to each other. The next characteristic we have is about the velocity. What is the velocity of the wave? Velocity of the wave we can visualize typically as a linear distance which is travelled by a wave in 1 second. That is typical velocity, is a general term, we know that, distance travelled per unit time. Similarly, here also, that means when the wave is moving, how much of distance does it travel in a given time, that is 1 second, that is called as a velocity. And that velocity in meter per second can be obtained by multiplying the frequency in second inverse by the wavelength in meters. So, that is the way we can compute the velocity of EM radiation by this velocity v is equal to frequency per second and wavelength in meter. So, essentially our velocity will be in meter per second. So, that is a typical unit of velocity we all know of. Then essentially our velocity is equal to frequency into wavelength, that is the way we can look at it. The next characteristic of our EM radiation is energy. Energy essentially can be seen to be dependent on the frequency and the wavelength both, and we have a very famous, a very well known equation for this which relates energy and the frequency and the wavelength. So, these are the equations which we will be using n number of times as we proceed in our understanding of spectroscopy. That is, these are fundamental equations. E is equal to h nu, where nu is the frequency, h is Planck's constant. So, E is directly proportional to frequency. And the second relationship is that E is equal to h c by lambda, where h is Planck's constant again, c is the velocity of light and lambda is the wavelength. So, what you see is energy is related directly to the frequency, more the frequency, more the energy, and it is inversely related to the wavelength, more the wavelength, lesser the energy. This is very important relationship we have to keep in mind. So, this is h is the Planck's constant 6.626 × -34 joules second, and c is the velocity of light in terms of 3 into 10 to the power 8 meters per second. So, energy is directly proportional to frequency and is inversely related to wavelength. This basically, this table summarizes all the characteristics we talked about. Wavelength in terms of lambda, units are meter and so on and so forth. Wave number is inverse of wavelength, again in meter inverse and all. Frequency is equal to c by lambda. Velocity is nu into lambda. Energy is hc by lambda. So, we see that the wavelength is the most crucial component. So, you can see that all the characteristics are related somehow to the wavelength. That is the most fundamental kind of characteristic of the wave, electromagnetic radiation. Now, this is just about electromagnetic radiation in general, but there is a broader term called as electromagnetic spectrum. Now, let us look at this picture. You must have seen this picture n number of times right from your school days. What this tells you is, this basically gives you a spread spectrum of all possible types of EM radiations we have. So, what you see is this, you can have various versions of this kind of a representation. So, what you see that this is your increasing wavelength. So, this is a very low wavelength, and as you proceed like this, wavelength is increasing, and in this side you are having increasing frequency. You can see that graphically also you can see that there is an inverse relationship between frequency and the wavelength. So, what you find is that on this side, when wavelength is very large, we have got long radio waves, that is what is used for transmission of radio signals, and then that is what you see for very long range transmissions and all. And then thereafter you have got radio waves like FM and AM that we typically use in our day to day entertainment, and then lower than that I am trying to come down in terms of the wavelength. So, I am starting with a very large wavelength, I am coming down to lower wavelengths. So, and also as you come down to lower wavelengths, energy is increasing. So, long radio waves are of very low energy, because wavelength is very large, frequency is very low. Frequency is low, energy is low. Okay. And then comes your microwave. Microwaves, we all know that is used for, I just mentioned earlier also, used for our mobile communications and also for our cooking as well. Okay. So, they fall in the range, they are somewhere lower than they are having wavelength larger than wavelength smaller than that of the radio waves, and energy of course the greater than that. Then next comes your infrared radiation, and then this small portion here, this is two lines here which has been expanded here, is your characteristic visible part of it, because that the whole range of colors what we come across, what we see, that is a visible spectrum, the rainbow, the whole thing is, we can see that this is just a small bit of the whole wide range of spectrum we have. As we go further down from the visible, we find that it is ultraviolet, and then comes your X-rays, and then finally comes gamma rays. Gamma rays are having extremely low wavelengths or extremely high energy. X-rays we know are very powerful, so are UV rays. What I want you to focus here on is this small portion of the spectrum here. You see that this is your visible portion, so called typical our VIBGYOR, the rainbow kind of a spectrum. In VIBGYOR, there is a red end here, next to red is your IR, infrared, so beyond red, and on left hand side here what you are seeing is ultraviolet, so other end is violet, so beyond that. So, what you see is that UV visible, that is the visible is your whole VIBGYOR, and then IR, they are very close in energy with each other, and they are the very crucial components in terms of our day to day routine spectroscopy measurements. All the radiations are used for spectroscopy, but they are the ones which are most readily or most commonly used for. Okay. More about it as we proceed further into different kind of spectroscopies. Now, what we just discussed so far was in terms of a kind of a wave, because the model, the way we visualize electromagnetic radiation was in terms of a wave. So, since it was a wave, there were characteristics of the wave accordingly. Now, you will recall that if you have understood, if you have learnt about quantum mechanics at some stage, you must have come across the quantum mechanical model of radiation, whereby this quantum model or the particle model says the radiation energy is considered as stream of discrete particles or packets of energy called as quanta, or in singular it is quantum. That is what was given by Max Planck to kind of account for a number of experimental observations like black body radiation, photoelectric effect and things like that. Okay. So, that is a quanta. So, typically from quantum mechanical perspective or for the quantum mechanical model point of view, EM radiation can be seen as a stream of particles called as photons or quanta. Light particles are called as photons. In general, they are called as quanta, because it is in general any quantum, any packet of energy will be called as quanta. Then since we have this, so this each quantum, each packet of energy is associated with some kind of frequency and wavelength, and its energy is given by the same expression what we had earlier, E is equal to h nu, E is equal to h c by lambda, or E is equal to h c nu bar, where nu bar is the wave number. So, these three are very fundamental relationships which we will be using time over again and again in terms of when you talk about spectroscopy, different aspects of that. So, this is very crucial. Next, let's take an example to see an application of this. Now, suppose I take up this small exercise. That is a radiation corresponding to green light, what you see as green light has a wavelength of 535 nanometers. Calculate the energy of photon of green light. Now, it is a very simple problem. So, what you have to do here is we have to know that we can recall that we know that we just mentioned that E is equal to h nu is equal to h c by lambda, and what I am given here is the wavelength, and the Planck's constant is known to me, the velocity of light is known to me. So, what I do is I just substitute them, that is all. So, what I get is substitute the values of these all the parameters, and I get energy to be equal to 3.72 times over minus 19 joules. So, that is it is very straightforward. That means, if there is one photon, that means one photon of green light will have so much of energy. So, that is the way we look at it. That is an application of this kind of relationship we talk about. Similarly, let us take up suppose there is a microwave radiation having a frequency of 12 gigahertz. So, now earlier exercise was we had the wavelength known to us, we are trying to find energy. Now, suppose I know the frequency, we can compute the energy of a photon, again a very simple problem to do, and then we can even calculate the wavelength of radiation. So, we can see the interrelationships of all these parameters. Let us see how to solve that. We know that E is equal to h nu. So, straightforward, our frequency is given to be 12 gigahertz, substitute that over here as 1.2 10 to the power 10 per second, and then put the value of h, the Planck's constant, you get the value of energy. It is very simple. Once you know the energy, then what we can do is we can, from this energy we can try to compute our wavelength. We know that we can use the second relationship here, that E is equal to h c by lambda. So, I need to find out lambda. So, what I do is I rearrange the equation. I get the following expression, that lambda is equal to h c by E. Then rest is very simple, substitute, because E we have just computed a minute back, substitute that over here, put the values of h and c and get the value of wavelength. So, what you get is the wavelength comes out to be 400 nanometers. So, what I am just trying to give a very small simple set of problems just to emphasize that the interrelationships between energy, wavelength, frequency and things like that, and they are very crucial, very important when you talk about different kind of spectroscopies. Okay. So, let us try to now quickly sum up what we have done today. What we have done today is we have just tried to understand what is spectroscopy, what is the domain of spectroscopy. We realize that spectroscopy is a study of interaction of radiation and matter, and it has got wide variety of applications across. Thereafter, we defined that we visualize EM radiation to be as oscillatory electrical magnetic fields which are travelling in the planes perpendicular to each other and also to a direction of propagation. And then thereafter try to understand the different characteristics which kind of characterize our EM radiation. They happen to be wavelength, amplitude, frequency, velocity, wave number and energy, etc. So, we have tried to visualize each one of them, then solve the significance of that, and also more importantly we have seen what are the interrelationships between them, because they are very pertinent, very useful for us at a later stage. And then another thing which we learned was, because all this I just mentioned to you was on the basis of the wave mechanical model or wave model of radiation, and according to the particle or the quantum model we visualize that radiation to be kind of a stream of discrete particles called as quanta. Singular is quantum, as I mentioned earlier. Now, in all these discussions here, I had tried to give you some kind of visuals, some kind of animations, and to show you that animations, I had used a software which is available in public domain. Anybody can be using it, they can download and use it. It is a copyright of Andras Slasky from Hungary, and this is the website from which you can download and make use of it. I have just touched upon some of the applications of the software. There are many more. You can talk about optical activity, you can talk about absorption, you can talk about a variety of things over there, but that were not relevant here, we not touched upon it. But it is strongly recommended that if you have access to it, get the software and try to use it, because it is a really very wonderful software to make use of. So, in the next session, what we will do is we will take up different types of interactions possible between radiation and matter, and to understand that we will also take up what is the nature of matter. That is, because we have learnt about radiation right now, we will talk about the nature of matter, and then we will take up what kind of interactions can take place between radiation and matter. And in the process, we will also take up something about what kind of prerequisites are there, because it is not that any kind of radiation can interact with any kind of matter. So, there are some kind of prerequisites are there. So, we will take up even that in the next session. That means nature of matter, nature of interaction, radiation and matter, and then the prerequisites for the interaction